Chair of the Department of Physics and the Director of the Center for Advanced Mathematical Sciences at AUB. And it's truly a pleasure to see so many familiar names, some that I have come to associate with faces as well, who have stuck with us for this series of multi-layered, multidisciplinary talks pertaining to glass. We're reaching the end of the series, so this is the next to last in the series for the semester. And I've already gotten a lot of requests to build on this work that we have done together, and we'll certainly consider opportunities and directions for doing so. Today's is a particularly pertinent talk by a fellow who I'm always keen on learning more from and collaborating with. This is Professor Shehadeh of AUB's Mechanical Engineering Department. Mu'tasim is an associate professor in that department, where he joined now since 2008. He spends his time trying to build algorithms to study the mechanisms of deformation of engineering materials with a view to applications to processing techniques. And when we say deformations, he covers them in various regimes, going from crystal plasticity to deformation under shocks, high strain deformations, dynamics of dislocations, as you can see, covering multiple scales, and all in one way or the other pertinent to the subject that brought this series together, namely glass in its multiple facets, and in particular glass as we've experienced it in our tragic explosion and fractures associated with these explosions. Without further ado, I will give the ground to Mu'tasim and just remind you that next week is our last lecture and you will be hearing more about it from us. Last but certainly not least, and we hope that you will all join and encourage others in your network to do so. So Mu'tasim, the floor is yours.
Thank you, Jihad. Thank you very much for this introduction, and the talk today is on the mechanical properties of structural glass, this is very important for us as mechanical engineers in the process of designing structural components that are made from such materials. And when we talk about design, we have to make sure that the components that we use in any application can sustain the mechanical or thermal load that is applied. In the case of glass, this is really of great interest, as glass, as you all know, is a brittle material, and when it fails in a very catastrophic fashion without any prior warning. So understanding these properties is very important, and there are many unanswered questions that are still under investigation regarding this aspect of the material. And in general, when we talk about engineering materials, since we're talking about glass, materials can be usually classified into families. Those families exhibit, each one of those families exhibit certain properties that are common to them. And in the case of glass, glass is usually, according to Professor Mike Ashby, is classified as the family of ceramics and glasses. These materials are brittle compared, for example, to metals such as steel and copper, where the material can undergo significant amount of deformation, and therefore they're ductile. They do not fail catastrophically, as in the case of these ceramic materials. Just for you to know, there are currently more than 160,000 materials, engineering materials, that are in use. So imagine this number. And again, these are classified into these four families of metals, ceramics and glasses, polymers and elastomers, in addition to hybrid materials such as composites and sandwiched structures. And as I mentioned, each one of those families exhibit specific and common properties. Those properties can be mechanical, such as stiffness, strength, toughness, ductility. It could be electrical, such as resistivity, thermal, such as heat capacitance or thermal coefficient of thermal expansion, optical and chemical, and so on. And the material property is directly related to its structure. And when we talk about structures, there are two things: either the atomic structure, whether the material is, for example, crystalline or non-crystalline. Some materials even are semi-crystalline, such as polymers, or microstructure, and that is the defect population in these materials and how they are arranged within it, and how do they interact with any external stimuli, whether it is mechanical, chemical, electrical, or even chemical. And in the selection of any engineering materials, including glass, after we look at the application, we have to make sure that the properties of such material will serve this application. And once determined, then we have to look into the processing. Is it possible that this material can be processed in shapes and geometries that are desired in that application? And then when the material is processed, its structure even will change. So the processing will affect the structure will affect the properties, and thus it will affect the application. So you have to make sure that all of these aspects are well understood and determined prior to the choice or to the selection of any engineering material, including, of course, glass. As we mentioned, there are four major families of engineering materials, and within the ceramics and the glass family, you can have also subfamilies. And here we focus just on the glass family, which in fact has many types, including the soda lime silicate. This is the most widely used glass. It is used in the manufacturing of bottles, containers. It is used in flat glass that's used in glazing, in windows, in doors, lamps also. Its composition is 75% silicon dioxide, that's sand, with some percentage of alkali oxide, such as sodium oxide and calcium oxide. Vitreous silica, this is pure silicon dioxide. It is amorphous. It is an amorphous material. It is not crystalline, although it can be made crystalline under certain processing conditions to make quartz. This silica is used for very limited applications, such as optical fiber or fibers and mirrors that are used in astronomy. The limitation in the use of this material is because of its melting temperature, which approaches around 2200 degrees Celsius. Another type or family of glass is called the borosilicate. This type of glass exhibit a very interesting property, and that is its coefficient of thermal expansion is only 1/3 that of the soda lime silicate. This means that if we increase the temperature of a sample made from this material by, let's say, 100 degrees, it will expand by only 1/3 the amount that a soda lime silicate sample would do. And therefore, this type of glass is used in applications where high temperature is involved, including, for example, the space shuttle, tile coating, household cookware, Pyrex, you all know that, or in glassware that are used in labs. And another important family of glass is the aluminosilicate, which is used in glass fibers. This is a composite material that has many structural applications. Now, when we talk about glass, in general, glass as a structure in terms of its atomic structure, consists of three different compositions. The first one is called the network, which is in this case the silica. And added to this silica is a modifier, which is usually an alkali oxide. Silica on its own, as I mentioned, has a temperature or a melting temperature that is around 2000 degrees Celsius. By adding this modifier, in this case, the sodium oxide, the structure of the silica will change so that some of the oxygen atoms, which are here the white circles, if you can see it. As you can see, each oxygen atom is connected to two silicon atoms. By adding this oxide, some of those bonding between the oxygen and the silicon will be broken, and therefore the melting temperature, this will lead to the formation of many non-bonding oxygen atoms, and therefore this will reduce the melting temperature of the material. The third component of glass is called the intermediate, which is usually metal oxide such as alumina, and this can be either a modifier or it can work as part of the network. So with this, we can move to here the way that flat glass, which is the most widely used glass in structural applications, produced. And here there are four major steps in producing the glass, in this case, the flat glass. So first, the batching, where the compositions are determined, and then they enter into a furnace that will melt these materials, and the material then will be flown into a bath that contains a molten tin. In this case, the molten glass will float on top of the molten tin in a process similar to oil on water, because the density of the glass, of the molten glass, is less than the density of the molten tin. And during this process, the temperature will be reduced to around 600 degrees until we reach here what's called the annealing chamber. And this annealing chamber, then the glass will enter it and it will cool slowly until it reaches the region where it will be further processed and cut. And with this, after the glass is manufactured, it can be treated further. So if it is not treated, we call it an annealed glass. In this case, the glass is allowed to cool down very slowly. This type of glass is the weakest of all glasses. When it breaks, I think this is very familiar to you. When it breaks, it will break into big pieces, and thus it can cause injuries to people when it does. And it is used mostly in windows and doors. If this annealed glass is heat treated, the strength of it can be increased by about 2 times. This can be done if by a process called heat strengthening. So the sample that is annealed can be then heat treated. It can be heated to a degree close to 650 degrees, and then rapidly cooled to room temperature. With this, the strength will increase by a factor, as I mentioned, of 2, and the fracture pattern of such samples will be similar to what you see here in the figure. It is very similar to the annealed case, but the size of the fractured pieces will be smaller. Now, there's another process that's called tempering. So in this case, the annealed sample will be heated to around 650 degrees, but then will be very rapidly cooled at a rate that is higher than the rate that's used in the heat strengthening. In this case, the strength of such glass will be about 4 to 5 times than the strength of the annealed samples. And when it breaks into very small pieces that will not cause harm. And that's why this type of glass is called safety glass. It is used, for example, in slide doors. And the fourth type of structured glass is the laminated structured glass, which is made by sandwiching 2 substrates of annealed or heat-treated or strengthened glass samples with a layer of PVP, that's polymeric material. And here the sandwiched polymer, which can be seen here in this figure. I'm not sure if you can see my cursor here. This thin layer of the PVP will absorb the energy of special of impact, and that's why such type of glass is used in windshield of cars and vehicles. Now, we mentioned here a process that's called tempering, glass tempering. This is probably the most important processing method for glass. And as I mentioned in the previous slide, by tempering the glass, its strength can be increased by a factor of 2 to 4. And the process here is based on introducing a favorable compressive strength in the material, in the glass samples. So let's look at here, if you like, at this figure of an annealed glass. Glass contains a large population of cracks on its surface. Imagine that this sample now is subjected to some bending moment. The lower part of the sample will be under tension. The upper part of the sample will be under compression. And since we have cracks and there's a tensile load acting on it, that crack will open, and thus if the stress created by the moment is high enough, the crack would propagate and it would lead to full fracture of the sample. Now, by heat treatment, a favorable compressive stress can be introduced on the upper and the lower surfaces of the sample. So now the lower surface has a residual. So before we load it, there is some residual stress already there, and that residual stress is compressive. And since crack will prefer, or they need tensile loads to propagate, then upon the application of the mechanical load, first we have to overcome this compressive residual stress before the crack can propagate. So this is the the mechanics, the basic mechanics behind this tempering process. And now I'd like to show you a video related to this issue of tempering. I'm sure you know these guys. So
watch this.
Watch this.
Yeah, this hot stuff is your basic everyday soda lime glass. There's nothing remarkable about it except that it's white hot and molten. I'm going to drop it in cold water. It's called a Prince Rupert drop. Who's Prince Rupert? Some variant from the 1600s. He came up with this. Okay, so there's a few things going on here. The cold water rapidly cools the exterior surface of the glass, hardening it almost immediately. The interior, still molten, cools more slowly. As it cools, it contracts and attempts to pull the surface in with it, but it can't. Well, not very much. The surface is already hardened, so it gets pulled in only a little, compressing it, while also creating an internal layer that remains forever under tension. It is this action that gives the glass its uncharacteristic strength. We call it compressive strength.
It sounds like the same principle as how an arch provides strength in structural engineering.
Yes, kind of. Now, Jamie, I'm going to ask for your help. We're going to attempt to destroy this Prince Rupert drop. I just want you to tip that hammer past its center point. Go ahead.
I feel like we've been swindled.
Swindled not. We have just experienced the power of compressive strength. It does, however, have an Achilles heel. Take those nippers right there and nip the back side of the tail of this Prince Rupert drop and watch what happens. Wait. Cue the high-speed camera. Okay, here we go. Oh! That was even cooler than I thought it would be. That is what happens when you release the stress in compressive strength glass. The whole thing shatters.
Spectacular.
Yes, well, at least in that example it was. That's
So I will stop here and move to the next slide here, in which we talk about the mechanical properties of glass. And here I'll cover three things or three properties. So first we'll talk about the elastic properties of glass, then the strength and the toughness. So when we talk about elastic properties, here we have to introduce two terms. The first term is stress. And stress is a measure of the internal force intensity that develops inside a solid material when an applied load is acting on it. And this stress can be either normal stress that it can cause elongation in the sample. So if you have a rubber band and you stretch it, you're applying a tensile load or normal stress on it that will cause its elongation. On the other hand, if you have, let's say, a piece of bonded blocks and you try to slide them one on top of the other, you're here applying a shearing stress on the sample. And as a result of the application of the stress, the material can undergo either a change in size, this is what we call normal strain, or a change in shape, and that's what we call the shear strain. And here, if you look at, for example, this cylindrical sample that is subjected to an axial force called P, upon the application of this force, the initial length of the sample, which is called here L0, becomes L. So there is a certain amount of elongation called delta. If we divide this delta by L0, with that we define the normal strain of this sample. If we divide this force by the cross-sectional area, then the normal stress is defined. In the second picture here, what you see is two bonded blocks that are subjected to an axial force F. But when this sample fails, it will fail by delamination or by sliding. So in this case, the gluing material is undergoing or undergoes a shearing behavior that leads to its fracture. And one can also define here an average shear stress and an average shear strain for this sample. Shearing can be seen in many applications, including, for example, here the applications which involve fasteners and bolts. These type of mechanical or structural components, when they fail under the effect of shearing. Or if we have a punch rod that penetrates a sample, this sample is or undergoes a shearing behavior. Another type of load that is of interest to us is the hydrostatic pressure. That is when the component is subjected to the same level of stress from all three directions. This is, for example, the case if we have a submerged element in water. The stress at all faces of the component is the same. And this type of hydrostatic pressure will lead to a change in the volume of this element. And each one of those types of stresses, whether they are shear, normal, or hydrostatic, are related to the amount of straining, that's the change in the size, volume, or the change in the shape, by a certain elastic measure that we call elastic moduli. So if we focus on the first type of loading, that's when we have a rod subjected to an axial load, and we look at the behavior by which the stress changes with the strain. That is the force versus the elongation, if you like. Then the behavior in most materials will be initially linear elastic. It's similar to a linear spring, and therefore Hooke's law applies. That is, the force is equal to the stiffness multiplied by the deformation, or in the case of here the sample that we're talking about, it is that the stress, that's the force intensity, is related to the strain by a material property that we call the elastic modulus, or E. Elastic modulus, or Young's modulus, and that's another name for it. Now, upon the application of the load, one also would expect that the lateral dimensions of the elongated sample will differ. So the cross-section of this element here, its radius, will be smaller than the radius of the initial sample. And we can here see that the change in the lateral direction or lateral dimensions of the samples are related, in fact, to the change in the longitudinal deformation through another property that we call Poisson's ratio. This is also an elastic property of the material. So each material exhibits a specific value of Poisson's ratio depending on its structure. So if you look here at the stress strain behavior, which is shown here for three different types of materials, ceramic, metal, and polymer, we can see that the elastic modulus E, which is basically the slope of the linear portion of this stress strain plots. You can see here that in metals, or for this metal that is shown in the figure, the elastic modulus is smaller than that of ceramic, but it is larger than that of polymer. So this elastic modulus is a measure of the resistance to stretching. So polymers are easy to stretch compared to metals. Some metals are easier to stretch than some ceramics. And in the same manner, we can define two other elastic properties that we call the shear modulus, or the modulus of rigidity, and the bulk modulus, which relates the hydrostatic pressure to the change in volume. That's in the case of the bulk modulus. And the shear modulus, it is a measure of the resistance of the material to twisting or to shearing. And if the material is assumed to be isotropic, as in many engineering materials, these properties are in fact interrelated. We need just two of those material properties to define the mechanical response of it. And here I'm showing a figure of how the Young's modulus changes in different material families. This is after Mike Ashby's mechanical or material selection in mechanical design. And as you can see, polymers have very small Young's modulus when compared, let's say, to ceramics here, and also to metals. And as you can see, many ceramics, especially the ones that we call technical ceramics, are stiffer than most of the metals, including steel. Non-technical ceramics, such as glass, have very comparable stiffness values or elastic modulus value to many metals, such as aluminum. Now, the elastic property or the elastic modulus of the material can also be related to the type of the atomic bond, and thus the atomic potential of the material. So here, and those, I'm sure that people in physics will understand this very well. Here, what we show here is the interatomic potential of a material, which shows that there is kind of competition between the repulsive and the attraction forces between them. And here, this solid curve shows the resultant repulsive attraction energies of the material. And of course, as you know from the first law of thermodynamics, any material will always try to be in the lower energy level. And this occurs at a distance that we call R0. So this R0 is the equilibrium separation distance or atomic distance between atoms in any material. Now, this energy, this is a potential energy. If we take the derivative of it with respect to the distance, what one would get is the binding force F. And at equilibrium, that's when R is equal to R0, that force has to be 0. That's equilibrium. There should be no resultant force acting on the element. However, if these bonds are stretched, so if the distance R increases, the force will increase. It will try always to bring the atoms to their equilibrium configuration. And if the level of the force becomes high enough, the bond could be broken, and this will lead to fracture. Now, if we focus on the second curve here, which shows the force versus the stretching distance, and we take now the derivative, which is the slope of this curve, what one would get is a measure of the stiffness. And this stiffness measure is directly related to the Young's modulus of the material. So what you see here as the slope that is obtained from a continuum large sample testing can be verified using atomistic simulations of if needed. With this, I can move now to the second type of mechanical properties that are of interest to us, which is strength. Now, when we mention glass, the first thing that will come to us is that glass is brittle. It does not show any ductility, which means that when it fractures with very little deformation. prior to its failure. But at the same time, being brittle does not mean that it is weak at all. In fact, the fracture strength of many glasses can exceed that of metals. Here I'm showing different types of glasses and their fracture strength. So in common glasses, the strength is about, ranges between 15 to 70 megapascal, which is comparable, for example, to materials such as magnesium. If we have tempered glass, the strength can go up to about 500 megapascal. That's stronger than steel. Glass fibers can exhibit a strength value that could reach 2000 megapascal. That's even stronger than tungsten. So glass can be very strong, but at the same time, it shows very little ductility. It is not tough enough. It is strong, but it is not tough. And when we talk about ductility, this brings us to talk about plastic deformation in metals. Why do materials deform plastically? And this is related, again, to their microstructure, to the type of defects that are present in such materials. And the main carrier of plastic deformation in crystalline materials is a defect called dislocations. This what determines the mechanical response of the material beyond the elastic limit of it. So materials like glass, as can show in the figure here, or aluminum oxide, which is a technical ceramic, they don't show any ductility, although their strength, again, is comparable to that of metals, because they do not have dislocations in them, or if they do, those dislocations are very hard to move inside these materials. And with this, we can talk now about the theoretical strength of glass. So if we imagine that we have a piece of fiberglass that is defective-free, it is manufactured such that the surface has zero defects in it, zero cracks in it. And we pull this sample in tension, as shown in this figure. One can prove that the stress required to fracture the sample is related to the surface energy. When the sample fractures, what happens here is that the mechanical force or the mechanical work that is done on it is transferred to form two fractured surfaces. So this mechanical force can be related to this measure of gamma F, that's the surface energy of the material, its elastic modulus, and its atomic distance. And with this, we can prove that the theoretical strength of glass is around 35 GPa, which is about 1,000 times larger than what is observed in experiments. For example, armored glass has a strength in the order of 350 mega. That's 0.35 of a giga. To reach 35 gigapascal, that's 1,000 times. So this tells us that fracture occurs because there are defects, there are cracks in the samples. And these cracks will lead to magnifying the stress around them. And this magnified stress will lead to the fracture. And here we're introducing a model that was developed by Griffith in the 20s, whereby an existing crack is assumed to be present in a sample, and that is subjected to a stress, a remote stress called sigma A. This stress here, which is applied on the surface, when we look at its effect around the crack, here it is an elliptic crack, what we see is that its value will be magnified by many orders of magnitude that will depend on the ratio between the distance C, which is half the crack length, and B, which is the crack height or thickness, if you like. So in the case of very small crack like a slip, this B value will be very small, which means that the C over B ratio will be in the order of hundreds or thousands, meaning also that the level of stress around the crack will be hundreds of times larger than the remote stress defined here as sigma A. And with this definition, we can show that if a stress level of about 60 megapascal is applied on a sample that contains a crack of a length that's equal to 50 micrometers only, then the level of stress will drop to only 60 megapascal, which is comparable to what's observed in experiments. And such investigation, in fact, was done using molecular dynamics simulations in which the crack size is limited to only 10 nanometers. That's a very, very small crack. And what is seen here is a stress and strain diagram of this sample that's subjected to a uniaxial tension with an edge crack present in it. And the load was increased incrementally until the sample fractures. And what is shown here is cases where a crack was not present at all. And with that, a stress level, which is in the order of 20 gigapascal, it's comparable to the theoretical estimate, compared to only 6 gigapascal when a crack size of only 10 nanometer was present. That's a huge drop in the material strength. So imagine now that the crack length was 10 micrometers, which is very easy to find in a sample of glass. So this brings us to the role of cracks, crack size, crack distribution. So the presence of the cracks, their length, their distribution is what determines the mechanical response, the fracture strength of the samples. And here a figure that shows how the strength changes with the depth of the flow or the crack in samples of different types of glass, including glass fibers, heat-treated glass, damaged glass that are used in many engineering applications. And what you see here on the x-axis is the size of the crack or the flow. So when the crack size is in the order of a nanometer, that's 10 to the 9, the strength can be in the order of few gigapascals up to maybe 10 gigapascal. When it is in the order of a micrometer, that's 10 to the minus 6, the strength drops to only few hundreds of megapascal. The issue here, though, is that in any glass sample, there is a distribution of cracks. There is a wide, in fact, distribution of crack lengths within the samples, and one cannot define a fracture strength of glass samples as a number. This has to be associated with a reliability factor. So we cannot say that the strength of this sample is, let's say, 50 megapascal. We have to say this is 50 megapascal with a reliability of 50% or 70%. When we talk about reliability, is the probability for the samples to fracture under the effect of a certain level of stress. And to illustrate this point here, we're showing here in this figure a range of strength or stress, failure stress of a number of fractured glass samples that are made from the same material. So what we see here is that there is a huge range, a very wide range of strength values between 25 megapascal to around 300 megapascal for the same type of glass, for the same material. And this shows or can be explained again by the statistical nature of failure. We may have a glass sample that has a crack size, let's say an average crack size of 50 micrometer, and another sample that's manufactured in the same process, maybe having a crack size of the order of 10 micrometer. Both of them will show different fracture behavior, fracture strength value, due again to this statistical nature of the crack length distribution. And again, this is related to this fracture strength, which is equal to the surface energy multiplied by the elastic modulus divided by C. So the fracture, the elastic modulus and the surface energy for all the samples are the same. They are the same material. What differs here is the length of the crack. That's the parameter C. As C increases, the fracture strength drops. With this, we can move now to the second measure that's used in the design of brittle materials in general, and that is the fracture toughness. So this parameter, sigma f multiplied by the square root of the crack here, is in fact a material constant. That's because the surface energy and the elastic modulus, as long as there's no change in the environment, there's no humidity maybe in the samples, this value here is constant, which means that this stress multiplied by the square root of the crack length is also a constant. And we call this parameter the stress intensity factor K. If the level of the stress for a given crack length increases so that it leads to fracture, we call this the fracture toughness of the material. So for a given crack length, the stress has to be increased so that the crack will start to propagate, leading to a complete failure. And that's what is used in the design as a design criteria. That is the fracture criterion in glass and in all brittle materials. And by looking here at this measure of the fracture toughness of silica glass, as you can see here next to the red arrow, the fracture toughness value for it is much smaller than those of polymers. It is much smaller than those of ceramics, of metals. It is smaller than those of composites. And that's, again, the main thing here, that is these materials are very, very brittle because their ability to absorb external loads, energy, is not that big. The energy is, in fact, dissipated in the process of crack propagation, as opposed to, let's say, a process of plastic deformation, which is the case in metallic materials and also in polymers. Now, with this, we have to talk about cracks, and there are, in general, 3 types or modes of fracture depending on the type of the crack. So what we were talking about in the previous discussions are surface cracks that are subjected to tensile load, as in the case called 1 here. So this is what we call the opening mode of a crack. The second mode is when the force is acting parallel to the surface of the crack, and we call this the sliding mode, or mode 2. of fracture. And the last one is the twisting mode of fracture. And by just focusing on the first mode of fracture and using advanced elasticity theory, we can find the stress distribution at the vicinity of the crack tip here. And this stress distribution is given here. And although there is only one component of the stress applied on the crack or on the sample, the stress state near the crack, in fact, is two-dimensional. So there are components of the stress in the X and also in the Y direction, and this stress level is, as you can see, is related to what we call the stress intensity factor, K. All right. So K divided by the square root of rho of R, which is the radial distance from the crack tip. So there must be some singularity in the solution, but that is, of course, not physical. And when the stress level becomes high enough, the material will propagate the crack, or in some cases it might induce localized plastic deformation in the sample. So with this, here we have the stress distribution around the crack, and this brings us to the topic of crack branching in glass. And I'm sure you experienced a piece of glass that is dropped on the floor, and by looking at the fracture pattern of such glass samples, one would see that the crack, in fact, branches. So the sample will disintegrate to multiple pieces because there is branching of the crack. And again, this occurs when the element is subjected to a kind of dynamic loading, as in the case of dropping a piece of glass on the floor. So in this case, branching takes place, and this branching is associated, in fact, or can be related to the release rate of the stored energy due to the impact. So there is a certain amount of energy, elastic energy, that's stored in the glass sample, but then creating one crack will not dissipate that energy. So the only solution for the material is to branch and create multiple surfaces. So instead of having one surface or two surfaces, we create four surfaces. So it's a bifurcation process. And using also elasticity theory, you can prove that the direction of branching is related to the stress distribution of the sample or near the crack tip. So here, what we are showing, or what's shown here, is the ratio of the crack propagation speed with respect to the longitudinal wave velocity. And what is seen here is that when the crack is moving very slowly, as in this curve, then the maximum stress will develop at an angle equals to theta with respect to the crack, so in this direction. However, when the crack is moving very quickly, let's say at a speed close to half the longitudinal wave speed, then the maximum stress will be at an angle close to 60 degrees. And that, therefore, when the crack propagates, it will propagate by branching along that angle. And again, that gives an explanation for this process of crack branching in glass, and as a matter of fact, too, in any brittle material. The last thing that I would like to talk about here is the strengthening of glass. And as we mentioned, strengthening of glass means that we have to introduce some compressive stress on the outer surface of the samples. And this can be done using the thermal tempering process. And in this case, the residual compressive stress that's developed on the surface can range between 40 to 180 megapascal. That's a very large level of stress. And the level will depend on the cooling rate during the tempering process. Another type of strengthening can be done also using chemical tempering, whereby in the case of soda lime silica, the sodium ions can be exchanged with a bigger or with bigger potassium ions. And since potassium is bigger, this will squeeze the region where they will occupy, leading to the development of compressive stresses in those regions. But the layer thickness that can develop is very small. When compared, for example, to the thermal tempering, where about 20% of the glass sample thickness can be strengthened. Here, strengthening can occur in a very thin layer below the surface in the order of 50 micrometer. This kind of chemical tempering, as you can see, it can lead to a huge increase in the strength, and they're used, in fact, in the windows of airplanes. This is the type of tempering process that's used in such applications. And with this, I will stop here, and thank you for your time and for listening.
Thank you, Mu'tasim. Thank you for a very friendly overview, keeping in mind our broad audience, and at the same time, evidently not being able to avoid the technicalities while explaining some of these difficult notions. So I appreciate the effort you put in establishing a balance, and I'm sure most people in the audience got something out of it, some perhaps more poetically than others. Thank you very much.
Thank you.
This was very kind of you. We have time for questions. An eclectic audience calls for a variety of questions. Feel free to cross-examine Mu'tasim, raise difficult questions from physics, from glass making. I see students in the audience, professors of physics. Questions, anyone?
Yeah, I have a question.
Aram?
Yes.
Yes, please. Please go ahead.
Great. So thank you very much, Jihad. Thank you, Mu'tasim. For me this is very interesting, and my question is in fact in two parts. The simple question is, how is, like, when you visit a house that was built, let's say 150 years ago, around or before 1900s, how would you characterize the glass that was used then, right? Very kind of primitive, but what in fact was its character? And the second part, which is probably more challenging or interesting as a question, is where is this going? So what do you expect glass to be like, let's say in 20 years? How is this going as a direction? I'm of course interested more in the thermal aspect, but I'm talking about the characterization of glass itself. Thank you.
Thank you, Aram.
Yeah, thank you, Aram. Regarding the first question, and that is, how do you characterize a glass that was made 150 years ago? Again, this type, for sure, these types of glasses were not manufactured using the float mechanism or method that I discussed in the fourth or fifth slide. These maybe were made by some kind of casting, that is to put the molten glass in a certain cast and let it just solidify and freeze. The process is similar, but the surface quality will be much different than the float or flat glass manufacturing process, in which one can control the population of defects in such materials. So in my opinion, if these samples are tested, again, with samples that are made from the same composition using the flat method or the float method, you will get much smaller strength values. Regarding your question, where do you see this going? I think this is a challenging question, given the many uncertainties involved in this field. At the end, here we're talking about fracture mechanics rather than deformation. Deformation is much easier to control. The mechanisms of failure to a large degree are well understood. In brittle materials, especially in materials that are amorphous like glass, there are so many factors that can affect the fracture behavior. The humidity can lead to huge drop in the material response. But however, is promising here is that the processing techniques in this field has advanced, whereby glasses can be used as an enforcing element with other materials like polymers, so which has huge technological applications. They're now widely used in many structures, very large structures. So I'm sure that this direction will continue to grow. That is the composite materials, where glass is used as an enforcing element or agent. Pure glass research, I think, is a very hot area. I learned a lot in preparing this lecture. And I know that there are many unanswered questions that will need, collaboration between theoreticians, physicists, material scientists, both experimentalists and people who work on computations. I think a topic related to materials by design, for example, can be of interest, whereby computer simulations, ab initio, molecular dynamics can help us understand what are the possible compositions that can be used instead of doing just trial and error. Let's try 75% silica with 10% sodium oxide, with 5% calcium oxide. I mean, this is just time consuming. It is not very effective, but the direction of using this notion of materials by design, where first principle calculations, molecular dynamic simulations with finite element can lead the experimentalist to decide on what composition should be used in a certain type of glass, that will lead to develop samples of required mechanical or thermal physical properties.
Great. We have a couple of questions in the chat.
Fascinating.
Thank you. So Sunnu is asking, what happens to these properties, I suppose glass properties, when different glass types are mixed, such as in melts or as sandwiches?
Sandwiches?
So he asked, what happens to glassy properties when different glass types are mixed, such as in melts or as in sandwiches?
When we talk about different glasses that are mixed in melts, what does it mean? It means that, let me go back to...
So what I mean is, if you take the borosilicate glass and the aluminosilicate glass and melt them together.
Yes. So instead of melting, let's look at the composition here. So both soda lime and borosilicate have 75% silicon dioxide, so that's fixed. What is different between the two is the amount of the alkali oxide, sodium oxide. It's 20% in the case of soda lime, whereas it is only 6% in the case of the borosilicate. So here, what you're saying is, what if we use the average value of these two compositions and melt them to make a new type of glass? I really don't know, because this is not, I think, a simple question to answer, because the properties are not additive. The microstructure, the type of bonding, will probably, I'm not sure, maybe drastically or slightly change by changing these percentages. So we have to try and see. I really don't know the answer to this question, but again, for sure it is not additive.
Any follow-up questions, Sunu?
Yeah. And I was also interested in when you sandwich them, that is, you take different glass layers and sandwich them without chemically melting them and fusing them.
Mm-hmm. So in this case, so let's say if we take a sample of flat glass that's made from soda lime silicate, with the same sample made from borosilicate, and we sandwich them together, and we look at the strength. Again, what will determine the strength is the weakest link in this case. So the one that has the lowest value of fracture toughness will fail, and therefore the structure will fail. This is, for example, different than when we talk about laminated glass. In laminated glass, there is a layer of PVP. It's a polymer, and this polymer will, in fact, absorb the impact energy subjected to, or the sample subjected to. In the case of borosilicate and soda lime, both are brittle materials. They both fracture in a catastrophic manner. And what will determine the strength of such structure is, again, the weakest link. Which one of those two, let's say, plates has a lower fracture toughness tolerance? This will lead to the fracture of that element.
All right, thank you.
Excellent. Another question in the chat, Mu'tasim. This one is from Sarah Najm. Yes. Can you give us an idea about algorithmic complexity when it comes to glass modeling? I guess this is right down your alley.
So, there are different techniques that are used in modeling glasses, and it depends on the length scale that you are after. So, if we're talking about understanding, for example, the behavior in thin fibers of glass, where the size of the cracks is in the order of maybe few nanometers, then molecular dynamics simulations can be used. Even molecular dynamics can be used to get some important information on the basic properties of the material, such as the surface energy of a certain composition of glass. The elastic properties also can be determined in a very accurate manner. When we talk about large scale or continuum level or macroscopic level type of simulations, then discrete method techniques can be used to understand the fracture patterns, the fracture strength of the material. A finite element using a method called extended finite element can be used to see, for example, the branching method or behavior, again, of large samples. So here the problem is dependent on the length scale that we are talking about, and that's why I think I mentioned the idea of using materials by design. That is to use simulation techniques at different length scale, starting from the electronic structure to the atomistic to the mesoscale, maybe using continuum or modified continuum theories to finite element to simulate the behavior of structural components of the glass. So again, if you're interested in the physics of the behavior, the underlying physical phenomenon, then one can use ab initio coupled with maybe molecular dynamics, or if you after the simulations of large-scale components, then we have to get some information from molecular dynamics that can be embedded in finite element to simulate and predict the mechanical response of or the physical response of such materials.
Sarah has a follow-up question. Sarah, would you mind asking it since it builds on what Mu'tasim was saying?
Sure. Thank you, Jihad, and thank you, Mu'tasim, for the very informative presentation. Just as a follow-up for the previous question that I've written in the chat, I just wanted to hear if you have a comment on this mesoscale modeling, like phase field crystal modeling, which couples the elastic field to a field depicting the crystallinity of the material in some sense.
Yeah, but here the issue is that glass is not crystalline. It is amorphous, and the couple here we're not talking about deformation processes. Rather, we're talking about fracture. So the issue here is related to crack propagation in such materials, the branching behavior. However, I mean there is some plasticity that is observed at a very small scale, and these glasses that will lead to what we call damage accumulation, which can be used to absorb some of the energy in such samples. So coupling these, since you mentioned the phase field modeling techniques, I'm not sure if it can be used in such applications. In my opinion, molecular dynamics, along with finite element, can lead to a much better, or discrete method can lead to a much better results or simulations.
Just a follow-up, if I may, as well. So these methods are definitely used in modeling crystals, but they're deployed in the use of amorphous materials, and they seem to be proving to be efficient. So I shared the link in the chat, and maybe we can follow up the discussion later, Mu'tasim.
Thank you.
Thank you so much.
Great. We have a question from Leonid Klushin. So he's asking, what is the range of glass transition temperatures for different types of glasses? And can one control the typical size of a crack by additional temperature treatment or surface modification?
I think the crack size can be controlled by the rate of cooling. So the rate of cooling can help in controlling the crack size of the glass samples. In addition to that, maybe adding certain oxides during the processing of the glass, during the manufacturing process. So finding elements such as maybe lithium oxide can help in removing some of these of the cracks, or maybe it can inhibit the formation of these cracks, or at least it can reduce or decrease their size. As for the range of the glass transition temperature, it depends on the composition, but I think it's in the order of 400 degrees, I think, if I'm not mistaken. It's within that range of temperature.
Any other questions, Leonid? Did you want to follow up on any of your questions? Okay. Question from the material scientists in the audience.
Hey, Jihad, I have a question, Malik.
Yeah, please.
First of all, thank you very much, Mu'tasim, for a very, very nice presentation.
Thank you.
I hope some of my solid state students were attending, but I guess they are still busy with their finals. I have a question. It's I was wondering if you know of any work in which people can incorporate crystalline domains, typically like nanocrystals within an amorphous glass matrix. So, for example, it could be something like silicon nanocrystals that are effectively crystalline with some properties within this amorphous network. I expect it to be a challenge for somebody who's trying to grow the material, but I was just wondering if this is feasible or if you've heard of such.
Yes, it is feasible, and especially the intermediates that are used in in making the glass, which are usually metal oxides like alumina. These materials, in fact, can precipitate, and they can form very small nano precipitates within the network of the glass So this, in fact, has been observed experimentally that crystalline precipitates of aluminum oxide is formed within the network of the glass. The role of this, I'm really not sure what does it exactly do. I know that it modifies the network. If somehow this alumina grow to certain critical size, I'm pretty sure that it can act as an inhibitor to crack propagation in the sample. So, but again, this is, I mean, these precipitates that were created are very small because the percentage of the intermediate is only in the order of 2% or less of the total glass structure. But again, these nano-sized precipitates were observed, and I think more research, more work need to be done to address this very interesting question, because this probably will lead to huge change in the overall behavior. Maybe it may lead to, again, increasing the strength. It can lead to crack blunting, or can begin the crack as it propagates inside the sample, and this will lead to an increase in the fracture toughness of the material. It's possible. But back to the question, yes, precipitates were observed, but with a very small size, in the order of 2 nanometers.
Okay. Yes, actually, I was thinking if it would be possible to have these nanocrystals with their properties within this matrix, and in a way, the matrix would be protecting, in a way, these nanocrystals, so that their properties can be conserved. So they need not necessarily be oxides, but I'm thinking maybe oxygen would be a problem.
We lost you, Malik.
Because if we incorporate something.
Can you repeat the last bit, Malik? We lost you. Okay. seems to be having difficulties. In any case, it sounds like it's the material for a further discussion and perhaps a collaboration between your two teams. Any other questions from the audience, students, glassmakers? Okay, I will ask one question. Maybe it would lead to others. You showed this beautiful video of compressive strength and the catastrophic failures it can lead to.
Yes.
I wonder whether you can, from your perspective as a simulator, take us through what's happening in the last few frames of the video when they carry out their beautiful experiment. Just walk us through it from your perspective as a simulator. Are we anywhere close to simulating what is happening in detail?
I think the mechanism.
We can replay it just to motivate.
Yes, yes. Let me do this.
Drop. Who's Prince Rupert?
I think we can move forward for the sake of time.
Hot stuff.
Yeah, this hot stuff is your basic everyday soda lime glass. There's nothing remarkable about it except that it's white hot and molten. Go, and I'm going to drop it in cold water. It's called a Prince Rupert drop.
Who's Prince Rupert?
Some Bavarian from the 1600s. He came up with this. Okay, so there's a few things going on here. The cold water rapidly cools the exterior surface of the glass, hardening it almost immediately. The interior, still molten, cools more slowly. As it cools, it contracts and attempts to pull the surface in with it, but it can't. Well, not very much. The surface is already hardened, so it gets pulled in only a little, compressing it, while also creating an internal layer that remains forever under tension. It is this action that gives the glass its uncharacteristic strength. We call it compressive strength.
It sounds like the same principle as how an arch provides strength in structural engineering.
Yes, kind of. Now, Jamie, I'm going to ask for your help. We're going to attempt to destroy this Prince Rupert drop. I just want you to tip that hammer past its center point. Go ahead.
I feel like we've been swindled.
Swindled not. We have just experienced the power of compressive strength. It does, however, have an Achilles heel. Take those nippers right there and nip the back side of the tail of this Prince Rupert drop and watch what happens. Wait. Cue the high-speed camera. Okay, here we go. Whoa!
Yes, that's it.
That was even cooler than I thought it would be. That is what happened when you release the stress in compressive strength glass. The whole thing shatters.
Spectacularly.
Yes, well, at least in that example it was. That's because the stress was so great between the outer compressive layer and the inner tension layer.
That when released, it was a catastrophic result.
Yes, I was referring to this stress release
Is good.
part of the experiment.
Yes.
Yeah.
So if you're talking about the solidification process itself, like you have a molten glass, it is cooled very rapidly so that the outer surface will be in compression compared to the core that will be in tension. You know, one can use, in my opinion, CFD, computational fluid dynamics, to simulate this behavior. Computational fluid dynamics, along with solidification tools like maybe the home code can be used for this. Molecular dynamics also can be used to simulate this behavior from the melt to the solid phase. In terms of simulating the behavior of the solid sample after it has solidified, after it has undergone the rapid cooling, this can be simulated using either particle methods, maybe finite element, in which fracture, XFEM, extended finite element, in which crack propagation can be also included, can be used for to simulate such behavior. So again, depends on whether we are talking about the solidification process of the molten glass to the solid, or simulating this fragmentation process due to the internal residual tensile stress that was developed inside the core. This behavior again can be simulated using either particle methods or finite element.
You mentioned, I think, potential for melts around cracks or plasticity. Do you allow for phase change in the course of simulations of these processes in your simulations?
In our simulations, no. The material does not undergo any phase change. So solid stays solid, and even if we're talking about a specific structure, that structure, crystalline structure, even will stay the same. So going from fluid to solid, or within the solid from a certain phase to another, is not within the capabilities of the techniques that we use. Not yet.
Okay, one last question, if I may. We've heard from many people who were present during the explosion. Of course, folks who experienced it very harshly, and those who also commented on it from their various areas of expertise, whether glass makers or stained glass experts or surgeons, and I couldn't help but wonder, as I heard you go over the talk, what would one of Mu'tasim's background think about as he either lived or followed videos of the explosion and its progression and aftermath? You can feel free to ignore this question if it's too troubling, but that's what came to mind as I was hearing you go through your lecture.
I mean, the explosion, was, of course, a very dramatic, very, sad event that took place. And in fact, when we saw all the damage that took place in Beirut, and the amount of glass that was broken, and the lives that were lost, many people who lost their loved ones, the people who were injured, I started to think mostly on ways. I'm talking here about personal perspective, because I work on dynamic behavior of materials, but it is mostly on ductile materials, shock and impact, which is what happened in Beirut. But unfortunately, this shock, destroy a brittle material, So what came to mind mostly is what could be done on these windows that are used in these buildings, so that you can make them maybe, of course, economical, but at the same time, you can make them impact resistant. Impact resistant materials or glasses are present, but they're expensive and they're heavy mostly. But the idea of making glass tough was one of the main ideas that I'm still thinking about But this would require a lot of research and collaboration with many people. Again, this is a very unique material, and understanding what exactly happens, how we can modify its properties to serve our needs will be a challenge that would require, again, the collaboration between experimentalists and theoreticians, and of course, materials modelers. So I hope, although the event was so sad, something good will come. At least from a scientific point of view, people will start to maybe to work on finding ways and discussing ideas to make these materials, tougher, so that God forbid, something such a thing happens again, the level of destruction will not be the same magnitude.
Thank you, Mu'tasim, for entertaining all our varied questions. I don't see any further questions in the chat, and I think we've exhausted you sufficiently. Thank you for very generously, once again, covering a broad range of properties for our audience. I hope you found it useful as much as we did. And I guess we can now close the session by inviting people to join us for the last lecture of the series, which will be held next week. Please note that there will be a change of time. We will remind you of that. In view of the time constraints on the moderator, the session will be moved to 6:30 p.m. and more on that shortly. So thank you all for joining us. Thank you, Mu'tasim, for your time and sharing of your expertise. And we will be seeing you next week, hopefully.
Thank you very much. Thank you. It was really a pleasure to be part of this series. Thank you very much.
Thank you, dear. Thank you all. Bye-bye. Bye.